Welcome to my new calculus channel. My name is John Gabriel, and today I'm going to discuss with you what are decimal expansions. In fact, a lot more than that. I'm going to tell you what radix expansions are. So let's begin. A decimal expansion is really just a representation of a number in a given radix system or base. So for example, in base 10, if we write 0.25, that's just a way of representing a quarter in base 10. But if we had to write it in, let's say, hexadecimal, then we wouldn't write 0.25, we would write 0.4, and you'll see why later on. So why would you want to write a quarter in a radix or base form? Very simple, so that you can do arithmetic like an automaton. Suppose that you want to perform the following sum: a quarter plus 3/8. If you don't understand what is a fraction and how fractions work, that's going to be pretty hard. So, given the following two representations, a quarter is equal to 0.25 in base 10. As you see, this little 10 here is a suffix. And 3/8 is equal to 0.375 in base 10. To add these radix representations, we simply align the radix point and then add the columns from the right, applying any carries that might result. And so there you see in front of you the method. So 0.625 is the sum of those two, without knowing anything at all about fractions. So on the other hand, to perform this sum using only a fraction requires understanding the derivation of rational numbers from scratch. That's quite a big deal, and it will take a long time to learn that. So how is a quarter measured in base 10? Well, there is a systematic way to do this. If you look at that template there in front of you, it's got powers of 10 to the left of the radix point and also to the right of the radix point. So the first thing you have to ask yourself is a quarter less than 1/10 or is it greater? So to determine the answer, you need to understand fractions. Radix arithmetic seems pointless unless you know the representations, which are 0.25 and 0.1, in which case you start comparing from the rightmost digits until you find the first mismatch and then make a decision, which is less or greater than. And if they're equal, you simply move to the next one and repeat the process all over again. So let's suppose there is a machine or another human who tells you the result of comparison for the time being. You are told that a quarter is greater than 1/10, so then you compare a quarter with 2/10 and 3/10. Since it lies between 2/10 and 3/10, you'll have to use 2/10 and make up for the difference in the remaining columns. It turns out that a quarter is exactly equal to 2/10 plus 5/100. So we can represent it using the template as follows. Simply place a 2 in the tenths column and a 5 in the hundredths column. If you carried around a template, you would have no use for the digit 0. Did you ever realize this? That means 0 would not be required in mathematics at all. In fact, we wouldn't even have to write 1/10. We could write it as 1/10 using some other notation without using 0. So, without carrying this template around, you would write 0.25. Okay, so can you tell why we write 0.25 and not just 25? Well, the answer is that we can remove this ambiguity because 25 can mean innumerably many other rational numbers without the use of 0. So the use of 0 is purely for human consumption. It can mean a quarter, 25, 250, 205, etc., depending on which columns you place the digits 2 and 5. Now, being the nice guy that I am, I'm going to show you a systematic way of converting fractions into any radix system. You've learned that long division is a means of doing this, but never understood because you never understood what division is in the first place. It's a form of measure. We measure the dividend using the divisor. In fact, all arithmetic operations are a form of measure, as I have explained in another video. So given a quarter, can you measure 1 using 4? Well, you can probably do this geometrically because you can divide any line segment into n equal parts, into exactly n equal parts, but you cannot do this in algebra. In algebra, the operation a quarter is equal to 1 divided by 4 is really a null operation. All that happens is the 1, or the numerator, goes to the top of the vinculum, and the 4 goes to the bottom of the vinculum. So P over Q is a rational number. There is no division pending. P vinculum Q does not mean P divided by Q. Division has taken place already. So all that long division helps us to do is to find a representation in decimal by measuring using powers of 10. And so you simply multiply whatever your number is by the base number over the base number. You're not changing anything there because that's equal to 1. Then you switch around the numerators. You're allowed to do this, and you know which property of the rational numbers allows you to do this. And you continue in this way until you basically percolate out all the coefficients, which are the 2 and 5, and the powers of 10. So this process stops when a repeating pattern is found or there is no remainder. As you've seen in this example here, there's no remainder. So now, using the method I just showed you, try finding a representation of a quarter in base 7. Well, you can say, does 4 divide 1? Nope. So multiply the numerator by 7 to get 7 quarters. Write the first part of your representation as 0 point and wait. Then, does 4 divide 7? Yes, it divides 7 once with the remainder 3. So write 0.1. Then multiply the remainder of 3 by 7 to get 21 over 4. And again, does 4 divide 21? Yes, it divides 21 5 times with the remainder 1. So write 0.15 and note that the digits 1, 5 repeat. So stop. Now, what you do in base 10 is exactly the same thing. If you had a quarter, you'd multiply by 10. And you'd say, well, does 4 divide 10? Yes, 2 times. How much is left? 2. Multiply 2 by 10. You have 20. Does 4 divide 20? Yes, 5 times. And that's how you get it in base 10, isn't it? So you can write that a quarter is equal to 0.15 recurring. This is not quite correct yet. We need a 0.15 to the base 7. Okay? This method is so easy you can learn to do it in your head. So now you've not only learned what is a decimal expansion, but what is a radix expansion. There is no such thing as an infinite radix expansion or an infinite decimal expansion. There is no infinite anything. Your educators do not know these things unless they learned the same from me. To understand what is a number for the first time in your life, read my article, How We Got Numbers, on LinkedIn. You will learn more than you learned in your entire school history. And that's pretty much it for this presentation. This is the New Calculus channel, and I'm John Gabriel. Till next time, goodbye.